So now we're going to switch our focus back to macOS. There have been a few talks that have mentioned detecting Mac malware, but I'm really excited for Annie's talk because it's going to focus on really detecting macOS badness malware through statistical analysis, focusing on command and control channels. So, round of applause.
So who's ready for some statistics? Woo! Perfect timing, you know, in the afternoon. It's better than coffee, I promise. All right, thanks everyone for joining my talk today. My name is Anje. I work as a data scientist, or I used to work as a data scientist, and now I've been working for 3 years or so as a detection engineer at a company called Adyen, which is a fintech company. And this is me in my first year of security, trying to look for these golden opportunities for data science. And now it's 3 years later, and I'm still working with heuristics and basic statistics 90% of the time. So this is actually a shout out for the universal and simple. I feel it's a good time to stick up for those, because we are trying to solve a lot of simple problems today with very complex models, and it's not always necessary. So I will try to show that with a pretty simple approach. With some simple statistics and heuristics, you can detect command and control quite effectively on your macOS. So a lot of you already know this, but just so we're on the same page, what is a command and control? It's a communication channel between the victim system and the attacker system, and the attacker uses this to interact with the system. And an example of a malware that uses command and control is Zuru. Maybe you know it from the Trojanized iTerm application. Yeah, it's good to know that not every malware out there will use command and control. It depends a bit on the objectives of the attacker. For example, if it's a simple set of automated tasks, it's not really needed to have this interactive channel, right? So simple malware won't do this, but a little bit more complex malware, like, for example, info stealers, they generally use this command and control channels. So back to Zuru. Zuru has leverages the open source framework Caffrey, or at least the latest version has been seen to do so. And Caffrey is a sort of an agent, and yeah, it's coming with a certain set of tasks, such as process execution or the ability to exfiltrate data. And a lot of the malwares out there, they leverage these open source command and control frameworks like Caffrey. And a very nice resource I can recommend is the c2matrix.com. It has, yeah, it basically keeps track of the open source C2 frameworks out there. C2 is, by the way, command and control. I should mention this. There are like right now 30 macOS open source frameworks out there. The most used language is Python, and the most supported protocol is HTTP. When you when the Caffrey agent is installed on the laptop, it will start a channel with the attacker and starts interacting every 5 seconds or so. This is called the beacon. And this is as an alternative to a constant live interactive channel. So it calls back to the attacker server with a regular request. And the big advantage of that is that it blends in better with regular traffic, makes it more difficult to detect. So how can we detect this in a universal way? Let me first try to explain what I mean with universal. There are 2 basic approaches to detection engineering that you see in general. You can either detect something that the adversary has or something that the adversary does. So that's signature versus behavioral. And then within behavioral, you can also distinguish trying to detect something which is very specific behavior to a particular malware, or trying to detect something universal, like the beaconing. Where I work, we spend most time on those universal detections. And that has to do with that, although there's value in both approaches, when you try to detect some very specific behavior, it can become a bit of a whack-a-mole game, because you're just one pivot away from the attacker and not detecting it anymore. For example, when an attacker changes its domain or changes the agent. Now back to the universal behavior that I tried to detect. And I already spoiled it a little bit. It's going to be about the beaconing, because the beaconing is not particular to Zuru. It's a universal thing that a lot of malwares will do out there. I think the majority of the malware will use this beaconing type of communication. Now, trying to detect it in a simple way. Maybe this was one of these golden opportunities for AI, right? And I know there are also a lot of great agents out there that do such a thing. But I usually try to approach things from sort of a first principle approach, because there is a trade-off when it comes to these complex models that's very relevant to security. And that has to do with the more complex a model is, the more of a black box it becomes. And what that means in practice is that you are not always able to tell why the model is classifying something as malware or not. And that also means that you not always know if you're properly protected against something. We're going to try first something in the middle, and starting with the simplest approach I can come up with. First time I was looking at beaconing, it looked something like this. So you see this repetitive pattern. And we're looking at an infected laptop. And I was checking out the DNS logs. And you're seeing these repeating requests towards the domain belastingdienst.com. This is the Dutch tax authority. And either this is a big lover of tax or something is up here. And if you are a native, you will see, you look very well, that there's a typo in there. So that sort of gives it away. And what also stands out is that the requests are regular, but they're not perfect. There's a slight deviation in there. Luckily, this was a red team, by the way. So it turns out that the beacon configuration is just a simple set of two parameters. So you have the callback and the jitter. And the callback is the repeating request that you're seeing towards the attacker server with the communication. And the jitter is the little bit of randomness in between. You can estimate the callback and the jitter in a very simple way. And this is nothing revolutionary, to be honest. The callback and the jitter can both be estimated by taking a certain mean. So for the callback, you simply count the number of requests and you divide it through the time unit. Jitter requires an extra step, so you take the second order difference, which is the difference of the difference, basically, and you divide that by the count of requests. And that gives you these two estimates that you're going to use, or that you can use in your detection. Now let's say you took a laptop and you monitored the processes on the laptop for a while, and you calculated these two estimates for each of these processes. So on top you see the 3 red dots. These are 3 malwares on the laptop, so it's clearly somebody who just clicks the links. And below you see expected processes. So Slack, IDE, the data backup. I'm more of a visual person, so I try to plot this on an XY axis to show you the principle of the detection. Our goal is to try to find the boundaries that distinguish these red dots, the malware, from the black dots, which are the expected processes that communicate. And there are multiple approaches for it. Some more complex, some very simple. We're going to again go for the very simple approach, which is common sense plus a bit of iteration. And the common sense part is that we try to detect basically the most stealthiest attacker with with an acceptable amount of false positives. So that means in practice that you try to find the highest boundaries that you can take. But the thing is, if you take the max of these data points, you're gonna end up with detecting everything. So that's not something you can realistically do. So you're gonna have to iterate, starting with the jitter, followed by the callback. So we would end up with something like this. Reality is not so perfect. This is just a very small data set, right? And if you're gonna start testing this in practice, you may end up seeing false positives. You see now the black dots appearing, right? Detecting something which is actually an expected process. Or the worst part, which are true negatives. And that means that you are not detecting something that should have been detected. And especially for true negatives, the only solution there is to test and test again, follow your threat intel, but also test this in practice and make sure like you test different C2s, different channels, and see if it's all false in the scope of your detections. There was also a point where I started to think about a more complex model, especially because once I started Monitor in this way, you could basically see, people do all sorts of things on their laptop, right? So people were querying the stock market, for example, or they were trying to get the latest results from Funda because they were looking for a house. And all of these things can be detected by that logic, right? So yeah, that made me think, but still I ended up with a very simple solution because it turned out to be very effective. And there's also a reason that I didn't want to take this risk. It's because it's pretty difficult to control that for example, if you take a machine learning model, that it's not learning from legitimate traffic in a wrong way. So this is, for example, also a nice resource called LolC2. And they're listing all the legitimate domains that are seen in the wild and also being leveraged as C2 channels. So we took a simpler approach, which is very specific heuristics or business rules. So we created a way where we could allow lists on the basis of process, even command line, the port it was using, etc. So you come up with very, very specific business rules, and that makes it hard to evade for the attacker. To my own surprise, this detection was very effective. So we did many tests with our internal events security team. We reviewed also threat intel to look at the callbacks and they were using. And also it's been effective in finding the red team. And the reason is this. Of course, you could set the callback and the jitter to an infinite number, but that has a consequence. Because it means that as an attacker, you need to wait a very long time on your results. And that's a very terrible experience, because imagine that you'd make a typo, and you have to wait for 2 hours for it to return. So as a consequence, what you see in the wild is actually a bit lower jitter and callback, because especially for endpoints like macOS, you don't have that time. Because the longer you are on the device, the more tricky it becomes. The user might reboot, do an update, or maybe in the meantime you do get detected. So in reality, this infinite sizes of jitter and callbacks, they don't occur so often. This is my message for the attackers out there. Just, lower the jitter and callback. Now to the implementation. And we implemented it with open source tooling. So if you want to, you can also implement this yourself. And I will take you through the data pipeline. We used OSQuery to query the data on the laptop of the processes and the socket events. and then we write it to a file, and that file is transported by Filebeat to an Elastic cluster. And on top of that, we use Python. We consume from this Elastic API, and then we can do the magic in Python, which is super flexible. OSQuery is a super neat tool. It's open source, and the nice thing about it is that you can query the operating system like a SQL database, basically. And what's especially interesting in this case, we're trying to monitor network events, which are very voluminous. And OSQuery allows you to do some exclusion logic, and therefore you're not pulling all the data all the time. And that makes it a lot better. And this is an example of how these OSQuery logs look like in OSQuery. This is one of the tests that our internal offensive security team did, installing SC2. And you can see it gives a very nice detail, showing the path, showing the process, the parent, the port, but also the PID, and all of these values will be there. So that makes for a very actionable logline. Python is really where the magic happens, because it allows you for all the flexibility. So you can do the little calculation that I just showed, but on top of that, we also pull a lot of other data on top of it, like the type of job profile that people have, which allows for even more specific exclusions. And yeah, that is the great thing about Python. And this is what the final alert looks like in our theme. We have our own build theme, as you might get from this story. We like to build everything ourselves. For us, this is a very actionable alert. It contains all of the things that you need to respond and to investigate it properly and make sure it's actually a true positive. This is how we do it, and it's work. But it works really well for us, and it's especially because, yeah, looking through all your network data in this way makes you really understand your environment, and also understand how the attacker works. It gives a lot of control, because the thresholds and the calculation, the thresholds and the business rules are explicit. So you know exactly what's detected or not. If a new malware comes in with a certain threshold and behavior, I will be able to say whether this falls within our detection logic or not, and I can tweak accordingly. And it's also very tailored to your own environment, which has a lot of advantages as well. But it's work, as I said, and it requires baselining and maintenance. I hope I could have convinced you of the universal and simple, and yeah, that this still deserves a place in today's world of AI, because it provides us a lot of control. I'm interested to hear your thoughts, how you do it, the universal detections that you use, so please come to me at the conference or reach out to me. And if any questions, if there's time for questions, there's time, then this is the moment. Oh. Yes.
Did you look at any malware samples where you were either impressed or surprised with how they did beaconing? Maybe it was like something that was unusual, or is it all kind of the same?
I was not so impressed, to be honest. I thought they were having quite high callbacks, and I guess because they don't have the time. Yeah.
So would you recommend they be more patient, or what would you suggest the attackers do?
I'm not gonna go into that.
What were you finding for your detections was like a useful minimum threshold for number of requests to get a pretty strong signal on detections?
The threshold, I will not share for obvious reasons, but I also think it depends very much on your environment. And I would even say that it depends for us per machine, because we use the same logic also on, for example, our Linux servers. And that's a very different environment with a lot of API calls. So you end up with a different threshold. So yeah, it's a custom approach per environment. So even if I share the thresholds, it probably is not going to work the same. It's more of an optimization problem. You try to find in your environment what you can take with a certain number of false positives. You want to have the highest number, basically.
Did you say you had to do anything like binary heuristics, like how long something can be on a disk, or signed and unsigned? Did you have to do anything there, or?
I was surprised, but no. This works pretty pretty well, but there is a baseline, right? So I think it's more on the allow listing very specific processes and their command line and their parent and their port. Because we know like Slack will always communicate on a certain port towards a certain domain with a certain command. So that's how we deal with it. So we didn't have to look into signatures or something more complex. Simple notebooks and making a lot of count plots, and yeah, starting with the big numbers, and then at some point I deployed it, and then things came in per week or per day, and yeah, it is a process, but yeah, basically started with some counts and some pandas data frames. um, I think maybe 2 weeks, and then I would say it also, we continuously maintain it, right? Because we still see false positives from time to time. But it's not so bad. I think we don't see many alerts, maybe one a week. So it's really doable for us to maintain the baseline, basically. Yes. Oh, good question. Um, Well, there was recent work by my colleague actually, which I really liked, and was also on C2, which was a long-running TCP connection, which is actually not in scope of this one, right? Because I only talked about the beaconing, and then you still need to figure out a way to detect these long-running interactive sessions. So yeah, that's an interesting one. Maybe you can give a talk next year. Yeah. Ooh. I have to say I don't have this in top of mind, so I don't know how much data we train on. Do I know the false positive rate from the top of my head? No, no, sorry. Okay, thank you.